Hello students. So in the previous class we were sort of looking at the application of vector calculus in mechanics, and we tried to derive equation of or formula for momentum, angular momentum, Newton's second law of motion, and we saw that the force P can be written as m times acceleration, where m is the mass of a particle and P is the applied force or impressed force, and A is the acceleration of the particle. So, today we will try to derive some equations of motion, where we see how vector calculus is useful to write the equation of motion of such particles moving under some physical law, and we will try to derive their path and things like that. So, let us start with. So, in the previous class we had this formula P is equals to m a, and this formula was obtained, which is basically called as Newton's second law of motion, and sometimes people also call it as equation of motion of a particle. Now, let us start with our very first example, example 1. So, motion under gravity. So, motion under gravity means suppose you dropped a particle or you threw a particle, then after a while when you throw a particle, then of course, it starts more or less in a straight line manner, but over the time it follows a parabolic profile. So, it mainly because the particle because of the gravity falls on the ground. So, basically the gravity at that point is acting as a force, and it is pulling the particle down towards it. So, it does not matter what kind of force you have applied, it may go far or it may fall right next to you, it will always follow a parabolic profile. And we will try to derive that that parabolic profile, and we will first see how we can do that. So, suppose we have a moving particle. So, suppose if we have a moving particle, if a moving particle of mass m be subjected to the action of gravity alone, then the equation of motion of the particle. So, equation of motion, as you remember, P is equals to m times A. So, A is the acceleration and P is the force, and the force is given by m times d square r by dt square, right. So, the force is given by m times d square r by dt square, and the right hand side is minus m g k, where k is the unit vector drawn vertically upwards. Right. So, now if we cancel m from both sides, then this is basically our d square r by dt square is equals to minus g times the vector k, and if I integrate both sides, then in that case this will be dr dt, which is basically our velocity v. Dr dt means v, and this side will be minus of g t k plus some constant vector b, and if I integrate again, then in that case this will be r times r. So, r is equals to, so if I integrate again, so r is equals to, this will be minus g t square by 2 times k plus b t plus some vector c. So, let me call it as equation number. So, this is our equation number 1, this is our equation number 2, this is our equation number 3. So, I integrated both sides of these equations, and when you integrate, I am assuming you are familiar with the ordinary differential equations. So, I integrated with respect to t. So, we will get a constant vector b, and then I again integrated, and then I got a constant vector c. Now, we have to find the values for b and c. So, the values will be, so if so when t equals to 0, so when t equals to 0, so when t equals to 0 at time t 0, at that time the velocity v and the initial velocity would be same. So, the initial velocity at t equals to 0 is same as the velocity v. So, I can write v equals to u. So, u is my initial velocity. So, then from 2 we will have what do we have? So, v is equals to u, this term will be 0 and b. So, this will be v u equals to vector b. So, if I use this in this equation, so I can substitute u here. Now, when t equals to 0, now again when t equals to 0, then the vector r will be 0, because when t equals to 0, then the particle is not moving. So, at that time basically the position vector r would also be 0. So, when t equals to 0, r is equals to 0, and then from 3 we will have 0, and here we will have 0 0. So, c is also a 0 vector. So, c is equals to a 0 vector, not implication, but we can write that is c equals to 0. Therefore, from 2, therefore, from 3 actually, therefore, from 3 we will have r is equals to minus half g t square k plus what do we have u t, u is the initial velocity and c is 0. So, this is the required equation of the motion of the so this is the required how to say locus of the point P. So, I can write the locus of R is a plane curve on the plane determined by the vectors determined by the vectors u and k and the origin. So, the origin and the vector u and k will determine the locus of R, and if we consider and so this is the required equation of the particle P actually moving along the curve, and basically this is the equation of the curve along which the particle is moving. And if we consider so one particular case, so if we consider u and k as the x axis and y axis respectively, then from this one is equation number 4, then from 4 we find that, so if we equate, so here I can substitute basically so if it is x axis, then this one will be u comma 0, and if it is y axis, then this will be just 0 and 0 comma k, and then I can equate the coefficients. So, basically we find that x equals to mod of u times t and y equals to minus of half g t square. So, eliminating t. So, if I substitute for t here, so this will be x by u. So, eliminating t will be, so eliminating t would give y equals to minus of half g by mod of u square x square. So, this shows that the path is a parabola. So, this shows that path is a parabola. So, that means when you throw the stone or a particle like this, then so if you throw like this, I do not know if you can be able to see in that video or not. So, if you throw like this, then basically your u is x axis and your k is let us say y axis. So, then in that case the particle is actually following a parabolic path, and that is what we were trying to establish. So, you see using just some simple concepts of vector calculus, we did not even complicate things. We were able to derive the equation or the curve along which the particle p, or in that case the stone p, let us say, move along that curve. All right. So, this is one of the interesting applications of vector calculus basically in mechanics. Let me see in my notes if I have anything else interesting to show. Next we can derive the harmonic motion. So, let me give you a small example. What do you mean by harmonic motion? So, equation of motion for the harmonic motion. So, harmonic motion so basically the equation of motion of a particle subjected to a force towards a fixed point, and with magnitude proportional to its distance, from the fixed point is given by, so basically what we have is, we have a, let us say, a closed curve. In this case we are choosing an ellipse. All right. This is our origin O, and let us say this is the point P, and this is x axis, and this is our y axis, and the magnitude is B, and here in this case the magnitude is A, and this is basically our mu times r, the position vector. All right. So, what it says is the equation of motion of a particle subjected to a force towards a fixed point. So, this is our fixed point O, and with magnitude towards a fixed point, and with magnitude proportional to its distance from that fixed point is given by d square r by dt square minus mu r. So, basically since this vector is r. So, since it is subjected towards that fixed point O, that means it is subjected towards that fixed point, that means that the vector is in the opposite direction. So, basically d square r by dt square is equals to, it should have been OP, but since it is subjected in the fixed direction O, then it should be basically PO, and that is basically minus of OP. So, when you change the direction of a vector, then in that case you have to put a minus sign. So, that is why you have taken minus mu r, or we have taken minus mu r, where mu is the constant basically. So, the general solution of this equation can be written as, so if you solve this equation, then basically the general solution can be given by, so if you solve this equation, then in that case this is basically you can assume r is equals to a cos t, r is equals to a cos t and vector a, and here cos, since we have mu, so this will be square root of mu t, and this one will be sine square root of mu t. So, if you substitute these solutions here, then it will satisfy this equation. So, this is basically the general solution where a and b are the arbitrary vectors, where a and b are the arbitrary vectors. So, this equation is similar to what we remember from our ordinary differential equation. So, d square y by dx square plus mu y equals to 0. So, if you solve this equation, then we usually obtain y equals to a cos root mu x plus b sin root mu x. So, it is the same thing. You can write r as the x plus xi plus yj, and then you equate the coefficients of I and j, and then you solve the individual equations, and then you sum them to get the vector r, and then you take a1 plus a2 as a new vector and b1 plus b2 as the second vector, and that's basically how you obtain this general solution. It's not complicated, but it's a little bit lengthy. So, I'm pretty sure you can be able to do that. Now, this is our arbitrary, and so these are our arbitrary vectors, and from this equation basically if we differentiate, then we will obtain dr dt, which is basically our velocity v, and this can be given as minus of square root of mu times vector a cos square root of sine square root of mu t plus square root of mu vector b cos square root of mu t. All right. So, these are the formulas, and if I choose at t equals to 0. So, when t is 0, then in that case when t is 0, then basically our r is this vector a. So, in that case r is the vector a, and v is, if I substitute t equals to 0, then sin t will be 0, and then this one will be cos t will be 1. So, v is equals to square root of mu b. So, square root of mu b, and so if the initial position, and the velocity is given. So, that means if the initial position and the velocity is given, we can fix up a and b. So, if we have the velocity of the particle and the initial position, let us say that vector r, then in that case we can fix up these constant a and b, and if the directions of, and if the directions of a and b are taken as x axis and y axis, then so if they are taken as x axis and y axis, then we can equate the first of all the coefficients from here, and then it is x equals to mod of a cos square root of mu t, and y is equals to mod of b sin square root of mu t. All right. and this will be basically, if I divide, then this will be basically x square by a square and y square by b square equals to 1, where a is equals to mod of a and b is equals to mod of b. So, if you choose x axis and if you choose vector a and vector b, those are basically our reference vector initially. So, if you choose those reference vector as x axis and y axis, then basically the curve along which the particle p is moving, for which it is it is subjected to a force directed toward the origin, the path which it follows is basically an ellipse. So, this is the path, or this is the curve along which the particle is moving. This is somehow also related to our planetary motion, that it follows an elliptic path, and the force, which is basically in this case the gravity acting between sun and the planets, it is actually directed towards that fixed point, and therefore, the path along which this planet is moving is basically an ellipse, or the curve is basically an ellipse. So, and a and b are the length of the semi major axis and semi minor axis. So, this is an important example which I chose to show you all. And do we have some other interesting examples? Of course, I mean, so here here I have a lot of examples actually, but if we try to cover all of them, then we probably run out of time to cover the other parts of the syllabus. So, let me give you another example, and I will leave the derivation of the equation for, or of the curve up to the students. So, it's you have to derive the formula for that. All right. So, the third problem is motion under the gravity subjected to the resistance proportional to velocity, So, first of all, motion under gravity, we know how to write d square r by dt square is equals to minus of m g k. Now, the thing is we have a resistance. So, that means when resistance against velocity. So, that means the particle cannot move freely, it got some kind of resistance. So, the resistance is actually a force which we have to subtract. So, it is a quantity, or it is a term that we have to subtract from this from the right hand side, because now you have got resistance, and since it is proportional to velocity, we can write it as m times mu times dr dt. So, that is the velocity, m is the mass, and mu is some constant of proportionality. So, mu is the constant of proportionality. All right. So, if you cancel m from both sides, then this is basically d square r by dt square plus mu dr dt plus g k. So, this is your required vector equation, or ordinary vector differential equations, I would say, although there is no such thing. You can call it simply a differential equation, or let us say ordinary differential equation in terms of vectors, and from here you have to solve this vector r. So, how to say, write these equations as x, y, z, and then if you try to solve it, then you basically obtain r is equals to we will obtain r is equals to ultimately. So, here I have a small answer. So, here we will obtain r is equals to, but I would ask you to derive this e to the power minus mu 2 u is the initial velocity divided by mu e to the power mu t minus g k times t times e to the power mu t divided by mu minus So, this is basically t e to the power mu t divided by mu minus e to the power mu t divided by mu square and plus c. So, c is a vector which we have to determine. So, this is the required equation of the path where we have to determine this constant c, and this is another example where we have used the vector calculus to derive the equation of the curve along which the particle is moving. So, like this you can have several examples from vector calculus where or from mechanics where you will have the application of vector calculus. So, for example, here I have the inverse law of attraction, then you can also write equations such as planetary motions, speed of a particle on any orbit, things like that. So, it's not just limited to these 2 or 3 examples, there are like thousands of examples where you can apply the concepts of vector calculus, or with the help of vector calculus you can be able to write their equation of motion and just try to solve to know the curve along which the particle is moving, use some initial conditions, things like that. So, we will probably stop this chapter here, because I think I have covered enough examples and gave you how to say enough idea where we use the vector calculus in mechanics. So, we will move on to our next topic, which is vector integration, like line integral, surface integral and volume integral, because we also have only 6 or 8 lectures left. So, I will try to include some examples in your assignment sheet, and you can solve them, and you are also I advise you to look into some vector calculus books where they are addressing some problems from mechanics, and practice them, and I am pretty sure you will be able to how to say learn some new things from there, and it will not be any problem for you. So, thank you for your attention for today, and I look forward to you in your next class.